Thank you, Chairman, for introduction. My name is Master Sistaninia, and today I will talk about improvements of strength and fracture toughness by utilizing spatial variations of the yield stress. Okay, first of all, I just give you a short introduction. As we know, energetic condition for initiation of crack growth is that crack driving force Jt should be equal or larger than Jc. Jc, which is called critical J integral, is a material property which can be determined by experimental fracture mechanics test. And Jt, or crack driving force, is a function of applied load, crack length, and geometry. For inhomogeneous material, crack driving force depends on a special variation, a special material property variations. So now the idea is a decrease of crack driving force due to a special material property variations leads to increase of crack growth resistance, and it means that in such case then we have to apply a higher load in order the crack can extend further. So the interesting is that this idea can be seen also in the nature. As we know, high fracture resistant biological materials, they have a kind of micro multi-layer structure consisting of hard layers and soft core compliant interlayers. Very interesting example is deep-sea glass sponge. This is a very
Could you please close the door? The speaker from outside is louder than you. Thank you. Excuse me.
This is a very tough nature composite, and if we look at the microstructure of this composite, you can see it's made of hard glass layers and very thin and compliant protein interlayers. So Professor Poletnik, using a numerical modeling, he showed that the strong variation of Young's modulus between the layers of this structure is the dominant reason for the high fracture resistance of this structure. As you can see, when crack enters to the protein interlayer, crack driving force is strongly reduced, and therefore crack is arrested by protein interlayers, and this is the reason why this structure is so tough. Okay, now this idea, the idea of enhancing fracture resistance by inserting compliant interlayers, which works very well in deep-sea glass sponge, can be transferred to technical materials. We have a hard homogeneous material, but now by inserting soft interlayers, we can enhance fracture stress or fracture toughness of our material. And this project, we only consider a variation of yield stress. In fact, interlayer has the same Young's modulus as a matrix, but it has a lower yield strength. So the design parameters of our multi-layer structure is the yield stress ratio. In fact, the yield stress of soft interlayers to the yield stress of matrix, interlayer thickness, and the wavelength of composite. In fact, the aim is we want to find the optimum configurations of multi-layer composite in order that the layer composite becomes strong and tough. Only I have to mention that for determination of crack driving force in homogeneous material, we have to apply the concept of configurational forces. Based on the concept of configurational forces, interface is also considered as a defect, and for example, when there is a crack in a beam material, in fact there are two defects, crack tip and interface. In this case, crack driving force can be determined as a summation of J4 and C homogeneity. J4 is a loading parameter. In fact, it's a driving force induced by applied load into a specimen. C homogeneity, or material homogeneity term, is a summation of all configurational forces which act on interface. When crack propagates into a more compliant or lower strength material, C homogeneity is positive. And in this case, J tip is larger than J4. And in this case, it means that interface has anti-shielding effect. But if crack propagates into a stiffer or higher strength material, seal homogeneity is negative, and J tip becomes smaller than J4. In this case, interface has shielding effect. Okay, when we have a specimen with a single soft interlayer, there are two interfaces, interface 1 and interface 2. Interface 1 has anti-shielding effect on crack driving force, but interface 2 has shielding effect on crack driving force. And in this case, the crack driving force can be determined by this equation. Now, let's look at the influence of the single soft interlayer on crack driving force. This is a very interesting figure. This figure shows the variation of crack driving force due to a single soft interlayer. As you can see, when crack has crossed soft interlayer, crack driving force is strongly reduced, and therefore crack is arrested at this position. In this position, which crack driving force becomes minimal, is called crack arrest position or CA position. And crack driving force of a crack located at this position is referred to J-tip CA. J-tip CA is a very important parameter for us in order to find out the design rules of more fracture-resistant multi-layer composite. So now we found that, okay, soft interlayer has influence on crack driving force. Now we want to find out the optimal configuration of multi-layer composite. The first question is, what is optimum interlayer thickness? Which thickness we should consider for soft interlayer? First of all, I have to mention that for qualification in order to quantity, the influence of soft interlayer, we define a new parameter which is called side interlayer. In fact, it is the ratio of J-tip CA to J4. And this, in fact, this parameter shows the reduction of crack driving force due to a single soft interlayer. In this figure, you can see side interlayer is plotted versus dimensionless loading parameter. In fact, it's the size of plastic zone inside the interlayer to the interlayer thickness. As for different yield stress ratio. As you can see, for all cases, side interlayer or reduction of crack driving force becomes minimum when the size of plastic zone becomes equal to the interlayer thickness. Therefore, from these results, one can say that optimum interlayer thickness is equal to the size of plastic zone, and it can be determined from this equation. So the next question is, what is optimum yield stress of soft interlayer? Again, by the finite element results, we found that the optimum yield stress of soft interlayer can be determined by this equation. In fact, the yield stress should be equal or smaller than 0.2 times the yield stress of matrix. And also from the numerical results, we found that a soft interlayer with optimum thickness and optimum yield stress can reduce crack driving force by a factor of 10, which is very interesting. So, up to now, we only considered a single soft interlayer, and we could derive the optimum configurations of soft interlayer. Now, the next question is, what is the optimum wavelength of composite? So, again, for multi-layer composite, the reduction of crack driving force can be quantified by psi multi-layer, in fact, which is the ratio of J-tip CA to J5. Here in this figure, you can see the psi multi-layer is plotted versus the load for different wavelength. As one can see, for multi-layer composite, the reduction of crack driving force is dependent on interlayer thickness, on load, and also on the wavelength of composite. By using the fracture mechanical considerations, we could derive the optimum wavelength of composite by this equation. I don't go to the details of the equation, but the optimum wavelength, can be determined by this equation. And as you can see in this equation, the optimum wavelength is load dependent. But a problem of this equation is that in order to determine the optimum wavelength, first we need to know the reduction or the psi multilayer of composite. And as I mentioned, psi multilayer is dependent on wavelength and is dependent on the load. In order to solve this problem, an iterative procedure is developed by us that by this procedure we can accurately determine the optimum wavelength of our composite. Not only 5-element computations, also in our group we conducted several experimental tests in order to explore the influence of single soft interlayer on fracture toughness. We conducted experimental tests on layered aluminum 7075 with soft pure aluminum interlayers. And for this multi-layer structure, according to the experimental results, we found that the fracture toughness of composite is around 20 times higher than fracture toughness of homogeneous aluminum material, which is again very interesting. So at the end, I have to mention that as we found that the optimum wavelength is load dependent, it means that by increasing the load, the wavelength decreases. The interesting is also, we can see this also in the nature. This figure shows a cross-section of the load of deep circulus sponge. As you can see for this nature composite, the wavelength decreases with the radius of the load. And as we know, the rods are under bending. And in bending, load increases with the radius. So it means also in the nature, the wavelength of composite decreases when the load increases, which is in agreement to our finding. So the conclusion of our work is that, first of all, we found that soft interlayers can enhance the fracture toughness and fracture stress of material, and then the conditions for maximum effectiveness of soft interlayers are derived. And also we found that by inserting optimum soft interlayers, crack driving force is reduced by a factor of 10, and the simple design criteria derived in our work, and then we found that the optimum multi-layer architecture is load dependent. Okay, thank you.